Thank you very much. And first of all, let me thank for the invitation here. It's of course a great honor. It's the first time. So I think we have all seen those photos or images. They have been, published in press with a lot of ado, and quite rightly. So the left panel shows you matter around the black hole in the galaxy known as M87, and the right panel shows you, and this is very recently announced result, shows you the black hole in our galactic center, which is known as Sagittarius A star. And those measurements, these are radio observations, have been announced and published by the Event Horizon Telescope. Now, the first thing that this tells us is that there is matter around black holes. We can detect matter around black holes directly. But of course, in order to infer any further information from such observations, we need theory. And what I would like to tell you about today is something about modeling matter around black holes, in the vicinity of black holes. And this will be a sort of theoretical physicist perspective. So my aim is not precisely to tell you how to model those data precisely, but what can those kind of systems tell us about physics in general, or at least slightly more. So when talking about theory of such systems, I think we should start with Kerr metric. So Kerr metric, it is a solution of Einstein equations, and basically it describes matter, the space-time geometry around black holes. It was discovered relatively late in the development of general relativity, because I think it was published around 1960 something, probably 1963, by Royker. Of course, I wanted to show how this particular solution looks like, so that you sort of grasp of what kind of mathematics we are talking here. But the important thing to stress is that this is a vacuum solution. So basically it represents space-time which is empty. There is no matter assumed, at least. And we solve, in order to get this solution, one solves Einstein equations, the equations for the structure of space-time, describing gravity, assuming that there is nothing in the space-time. And the assumption behind this solution is that you search for a stationary solution. And basically, this is the most important assumption, and the solution which is axially symmetric. And this particular one has a black hole horizon. So if you take into account or analyze how the light travels in this space-time, you realize that there will be a region from which no light can escape outwards. Now, this solution is also characterized by some mass and some angular momentum, which you can compute at infinity. And then from this, you can understand that there is something inside, and of course, you naturally associate this mass and this angular momentum with this black hole. Now, there is something known as the Kerr hypothesis. So this is a conjecture that tells you that astrophysically relevant isolated black holes are described by Kerr metric. This is extensively tested in all possible ways. It seems that this is the right one. But of course, what we mean by isolated here is that the system consists mostly of this black hole. So if you put matter around the black hole, it should not change significantly the space-time geometry. And so, in other words, it's not self-gravitating. It doesn't influence the gravity by itself. Now, I should have at least 2 slides to talk about how you could put matter in such a model. So, in general relativity, the main equations that you solve are Einstein equations. I don't know if I can at least show you this with a pointer, but these are those equations. And they, as famously stated, they connect the gravity component, well, the geometrical component that describes space-time. This is this tensor G mu nu, which is called Einstein tensor, with T mu nu, which is the energy momentum tensor, and which describes the matter component. So, for instance, this Kerr spacetime is obtained by setting this T mu nu to 0 by hand. But what else general relativity tells us is that is based on some geometric identities, which are known as Bianchi identities. And this is a theorem in geometry that this tensor, this geometric tensor, satisfies this type of equation, which has a form of conservation equation. And therefore, if you've got T mu nu on the right-hand side, T mu nu also must satisfy some conservation equations. And of course, you might not be working with this kind of mathematics, but let me just tell you that in Newtonian case, this type of expressions would have the form involving time derivatives and spatial derivatives. So basically, this works as equations of motion. And the way in which matter is modeled in general relativity and in relativistic astrophysics is basically based on the assumption on this energy momentum tensor. This is how you put matter model in all theories within general relativity. So what can you choose? For instance, you can choose as a matter model perfect fluid. So this is an energy momentum tensor, which you can assume, and basically this algebraic form would lead to hydrodynamics. Right? This would be the gas which would be described as you would describe water, right, or fluids. You could also realize that in this astrophysical scenario, the gas is plasma, so there will be electromagnetic fields present. And what you do then is you can take the energy momentum tensor of electromagnetic field, and you just, you go to your favorite textbook on electrodynamics and you take the energy momentum tensor from electrodynamics. There is a special framework which is called magnetohydrodynamics, which allows you to associate in more detailed way this energy momentum tensor of electromagnetic field with the one that describes fluids. And then you've got a framework of dealing with magnetized fluids. Now, I should also mention, for those who are working more with physics, but this is just a side remark, I would say, that there are only 4 equations stemming from Bianchi identities. So if your matter model involves more than 4 functions, which is customary for all more complicated matter models, you need to put some assumptions. And this you do more or less by hand, in a sense that this will be your physical assumptions on what you model. So for instance, if you want to have electromagnetic fields, you need Maxwell equations, of course. And if you've got more complicated fluids, you need to relate pressure to density, and hence equation of state would be needed. So what can you do once you decide on the matter model? For instance, you could put the resulting equations on the computer. You could choose some initial data and let the equations evolve those initial data and see what happens. The trouble, of course, with this is that this is more or less ad hoc, but this is how the majority of this theory is made, and how, for instance, the images that I showed you at the beginning are really interpreted. So this is a kind of pedagogical simulation that I did with some collaborators some time ago. There is a non-rotating black hole in the center. The metric is fixed, so this is like, this one is a Schwarzschild, but it could be Kerr. And you put gas with some initially added angular momentum. So the colors decode angular momentum. The more red the picture is, the fastest you rotate. And you start evolving, and you see what happens. And because this situation is unstable, sooner or later numerical errors will come into play, and you will see those turbulent motion. But if you take a look at how the density behaves, the density of this hydrodynamically described gas, then you would see that even though you started with spherically symmetric distribution, then sooner or later some kind of disk forms. And this is precisely what is sometimes referred to as the accretion disk. And this is in the vicinity of the black hole. This actually behaves more or less stable, and you can do a whole research in this line trying to investigate what happens later. But a physicist could do a little bit more. A physicist could think, what would happen if I really take self-gravity into account? If I imagine that this gas is actually quite massive, that the motion is not only governed by the gravity of the black hole, but if I allow this matter also to be a source of gravitational field. Now, of course, in theoretical physics, then you can play freely. You can imagine more mass, right, in the black hole component. The metric will be no Kerr anymore. And the model that, I'm trying to show you here is, for purpose, a stationary one. So we are solving the equations assuming at the beginning that the solution should be stationary, just to be able to, research more models in reasonable time. And of course, then if you do things rightly and you solve those Einstein equations, which are so complicated that you anyway have to do this on the computer, you will get some models, and you then can learn what, for instance, more magnetic field does. In this case, it shifts the most dense part of the disk towards the black hole. So here, we've got more magnetic field here, and the sensor is closer to the black hole and less here. You can also take, for instance, less matter, and then you will learn that those disks would become thinner and thinner, and so on. And this may be interesting, but there is nothing, extraordinary with this. But there could be some extraordinary things that can tell you something about gravity itself and this geometric structure of spacetime. So, for instance, if we allow to have more massive disks, then we discover that the solutions bifurcate. So for parameters that describe the solutions, you get more than just one. Okay? And this is quite interesting in this context, because it turns out that if you say that your parameters are, for instance, the maximum density within the disk, the black hole mass, the spin of the black hole, the inner radius of the disk, the outer radius of the disk, etc., then usually you find two solutions. And one can be a light one. And in this case, these are light solutions. There is mass on this, the total mass on this axis. And here the spacetime is Kerr-like. But you can also have, at the same time, very massive solutions. And this is quite strange, because what you assumed is that more or less looking from outside the geometry is the same. You've got the same maximum density and a huge difference in mass. So how could you understand this? Well, there must be something with the geometry of the spacetime and space itself. And one of the measures of this effect is to have a look at something that is known as circumferential radius. The circumferential radius is a radius that you associate to a circle simply by taking its circumference and dividing by 2 pi. So in standard geometry, this gives you the ordinary radius. So this would be a geometric measure of the size of the circle. So now you can take, say, more massive solutions and look at the circumferential radius as a function of your coordinate radius. In GR, coordinates can be chosen freely because a priori you do not know what the geometry would eventually be. But you can have then geometric quantities computed, and this is a plot of the circumferential radius. So the shaded region is a region occupied by the disk itself. And what you can see, and which is quite strange, is that there is a local maximum. So if you think about the largest circle which you could embed within the torus or disk of heavy matter rotating around black hole, you would naively think that this should be the outermost one, right? But it turns out to be wrong. There is one which is within the volume occupied by the disk, which is larger. And this shows that probably there could be an explanation of those strange bifurcation pattern in terms of geometry. So maybe another way to somehow visualize this and to grasp this and to make a contact with high school or even elementary school mathematics is to refer to the theorem that we learn at primary school, and which is, if you look at Wikipedia, it's known as Pappus-Godinus rule. And this is actually a theorem apparently known to Pappus of Alexandria many, many years ago, that tells you how to compute a volume of a solid of revolution, right? You take a plane figure and you revolve this plane figure around a given axis, right? And this theorem tells you that in order to get the volume, you multiply the surface of this plane figure times the path that the center of the mass of this figure in this geometrical high school language traveled. Right? So in this way, you can, for instance, compute the Euclidean volume of standard torus, right? This is a formula that you can get, and probably you then learn at school. And if you express it in terms of the inner radius of the torus and the outer radius of the torus, you get this familiar expression. Now, I could plug those circumferential radii corresponding to the inner radius of the torus and the outer radius of the torus to this formula. And I could somehow contrast the result with a true geometric formula, which I can, or true geometric volume, which I can compute if I have my solution. And this is what I get. What I learn is that, in fact, those massive solutions, they are massive, although they have the same, more or less, density, because they are simply huge. Even though, when you look from outside, you would say this is the same size as object. It has the same circumference and so on. Simply the volume is much larger than the one you would naively infer from, say, Euclidean formulae. So this is an example of how gravity works. If you allow for more matter, it really changes geometry to this extent. And this matter could be also a matter of, say, a disk of gas revolving around the black hole, as in this case. Okay. Well, so far so good. We can learn things from those hydrodynamical models with magnetic fields. But this is not the only description that we have at our disposal. I think that if you would think about gas and you would try to do some physics of gas around black holes, the first thing you would think about would be simply to put a bunch of particles and to think how they move. And there is a well-known thermodynamical description of matter going along this direction. And this is known as kinetic description or kinetic theory. And this can be also investigated within general relativity. And in the simplest, or probably the simplest but reasonable setup, this is nowadays referred to as the glass of gas. So you think of the gas as a distribution of particles, and this distribution is described in the phase space with some distribution function. So this distribution function more or less tells you how many particles you would find in a given point with a given location, okay, and with a given momentum. Now, one thing is to learn how to get this distribution function, so what conditions to impose to get the motion. And the other thing is to learn how to connect this kind of model with general relativity. And this is the second part is actually much more troublesome, I would say, and much more related to some physical assumptions, because as I was trying to tell you, in order to couple matter with gravity, we need to go through this notion of energy momentum tensor. And this one, in this case, is an assumption. So what we do is we assume that in order to get the energy momentum tensor, I have to integrate the momenta with this distribution function over the momentum space. So this would be, a field that would tell you somehow something about the matter content in a given location. I could also have a current which I would refer to as particle density current. And the other so basically what I was trying to tell you is that this is not obvious that this is the only way. This is an assumption, because if you think about the gravity of a single particle, then you would realize that this is a complicated thing. You do not know what this particle locally does. So the assumption here is that there is a gas of those particles and they move through space-time. And this would be the zero level of averaging. But for non-colliding particles, you could have equations for, and this would be the simplest case, you could have equations for this distribution function. And they stem from a requirement that if you travel along a path of the free particle, then this distribution function should not change. And in explicit terms, this leads to the so-called Vlasov equation, which has this form. And you can, and the plus is that you could also show that if you invest this equation, then the energy momentum tensor and this particle density current defined as in the previous slide would satisfy the conservation equations as they should. So everything is consistent here. If you allow the particles to scatter, then you should, instead of the zero here, you should put additional terms, and this would be a mess. I mean, really a disaster, but probably reality is somewhere in this direction, because, the previous approximation simply assumes some local thermodynamical equilibrium, which doesn't have to hold around supermassive black holes, for instance. Now, so I wanted to show some example of a calculation that actually can be done in this approximation, assuming zero interaction terms between particles. So the gas moves freely. And this model is a general relativistic counterpart of something which is quite old, and which is a model of a black hole traveling through a cloud of gas. This problem is known as the so-called Bondi-Hoyle or Littleton accretion problem. So you imagine you've got a black hole, you've got a cloud of gas, it could be homogeneous at the beginning, and you put a black hole and it travels through this cloud. And you are interested in answering what happens. This is a classic problem in relativistic astrophysics, but it has a very non-relativistic beginnings due to Bondi-Hoyle, Littleton, who were first investigating accretion on, say, Earth or Sun. And there were even papers in, I think, 1920s about climate variation. So this is the origin of this problem. And here the assumption in my case is that the gas is collisionless, that it is somehow thermalized at the infinity, where and then therefore it obeys the so-called Maxwell-Hutner distribution. And the plots that I will show are basically from the observer somehow associated with the moving black hole. So it turns out that you can solve all those equations, and even you can get exact solutions. And this is the system that you get. I can comment on all plots here. So in this system, you only take into account the particles that originate at infinity and go back to infinity. This is because you are talking about a cloud of gas which is uniform at infinity. There would be particles orbiting around the black hole that you could take them into account. You don't have to, because you assume that the gas is collisionless. But those particles which originate at infinity, they have two options with respect to the black hole. Either they travel towards the black hole and get, so to speak, scattered. They can, say, orbit a black hole even a couple of times and then get scattered to infinity, or they get absorbed by the black hole. They simply fall into the black hole horizon. And in order to have a full description, you take into account both classes. So the left column here shows you what happens with those particles which get absorbed. This is the column that shows you what happens with those particles that are scattered back to infinity. And the right column tells you what happens if you take into account a full budget and everything is computed. Now the arrows show the direction of motion of net motion of particles, and this arrow placed at the black hole shows you where the black hole moves with respect to the gas, right? And you can also see what happens if you change the asymptotic temperature. You can see what happens if you change the velocity and so on. Those plots show you the density, which is color-coded here. So the more red that is, the denser the profile. So for instance, what you can notice is that just behind the black hole, there should be a place where there is almost no matter. If you would like to have a perfect protection in interstellar travel, you just sit there and you know that no bullet from infinity can reach you. But it also tells you what happens in the front. There is this denser region, and if you are interested, you can investigate other properties. What this tells you also, all those calculations, is that, well, you could compute the mass accretion rate. So you could ask the obvious question, how much matter does this black hole accrete in its motion through the cloud of gas? And well, this is just referring to the kinds of mathematics that is involved. This is the answer in this case. And what's interesting here, and probably this is the only reason that why I'm trying to show this, is that in this case the answer is different as compared to the case where you would do the same hydrodynamically. So, for instance, in the standard hydrodynamical regime, which can be also recovered here for high temperatures, this mass accretion rate would grow with the velocity. Right? So the faster you go, the more matter you accrete. And v is the velocity of the black hole. But it turns out that if the temperature of matter is small and you do this kinetic approach, then you learn that there is a local minimum in the mass accretion rate. So there is a very high relativistic speed, but still finite. whether you accrete the least onto the black hole. So, yeah, I think it's time for a summary, because so the message to take home is that you could do some theoretical physics and investigate dynamics of matter around black holes. And I think it's a perfect context to study the behavior of matter in very strong gravitational fields. And of course, there is a link to observations, because you could try to make your model very much fit into the observations that you actually have at hand. But also, this is a playground where you could try to do something converse. You could try to learn something, for instance, about gravity and how general relativity behaves by simply allowing your models to, to do something that you probably do not observe at the moment. So, for instance, you put more matter and you see what happens. And I hope I convinced you that some strange gravitational effects can appear. Now, the last point, this is probably my main point, but it's common to physics in general. Even if you take a range of very conservative, but relatively, well, in this case, relatively simple matter models, then the results would very, very strongly depend on what you have assumed. So, of course, why I'm stating this, because then when you hear what how people interpret the observations, then of course this is very, very strongly dependent on what the models were used. So, of course, if you are more interested, then you look at the details. And this is still talking about very conservative assumptions. So there's no exotic physics, for instance, and this is another a branch of research which is also active. Okay, thank you.
Thank you very much. We have time for discussion. Do you have a question, please?
I have a question on the utilization of the properties of matter around black holes, or actually being swallowed by black holes. What is your view on the concept of the Google Blitz black hole?
I don't think I know what
it's a generator that utilizes radiation. That is it's a generator that utilizes the radiation produced by matter that is being spaghettified at the accretion disk of a micro black hole. It's a concept that is being rival to the Dyson swarm and so on, the so-called Kardashev futurology.
Okay. So let me put it that way. Within the standard physics, and everything that I'm talking about here is what I view as standard physics. That is just reasonable assumption within the best theory that we have. There are, of course, possibilities to extract energy from black holes. The point is, you would have to have an operational black hole somewhere near and be able to do this, right? So you would have to be this very, very, very clever civilization that can utilize those phenomena, and I don't think we can do this in any near future. But the mechanism should work.
Question, what's the rate of black hole evaporation, and is it dependent on? I'm not a physicist, and my question is the rate of black hole evaporation related to the matter it actually consumes? For example, if it flies through a very dense interstellar medium or swallows stars, does it have an impact on the rate of evaporation?
This is a good question. Evaporation in general is computed mostly by assuming that you've got a space-time metric given. And this is a different process that I was not discussing here. It's a quantum postulated process. So this is, not that much standard as the stuff that I have discussed here. So there are two effects here with respect to your question. One is that those processes clearly change the mass of the black hole. And the evaporation is another one that does the same, and they would sort of compete. And of course, they have to, one influences another, right? In theory, in just abstract setting, because the rate of evaporation is dependent on the black hole mass, right? So you could compensate. And another thing is, of course, that this is a medium. So then you've got evaporation, and this is radiation, right? So of course, this radiation due to matter could be dominant. So yeah, of course, there is interaction, but I think it could go many ways.
Okay, thank you.
Thank you very much. Question, please.
I wonder if there is any classification of black holes that you already can compute according to the mass. So there are big black holes, small black holes. Is there something like this in space?
The question is what you mean by classification. Do you think purely theoretical mathematical classifications or what people observe?
I wonder, for example, do we have some closer black holes in our galaxy, but we don't see because they are super tiny, super small, and they are not visible?
Okay.
I know this
is debated.
This is yes, but what do you think? What are your research maybe telling about this topic?
Okay, so I would say that people even could have an idea that dark matter is formed of black holes, right? So now, if this is exotic or not, I don't know. If I see a very convincing argument, that I would be convinced. What I'm convinced about are those astronomical observations that state there is the particular object and it best fits the idea that it's a black hole. Meaning there is horizon, right? That this is a space-time construction. So I would believe in those observations in the center of the galaxy. I believe in many candidates, which are, for instance, in binary systems, and right. This is the best explanation that would fit all the observations, and surely there are gravitational waves emitted by the binary system of black holes, and this I think is also widely accepted as the best explanation we could think, because this was an idea that we had much earlier, and then finally the observation of gravitational waves was confirming this and fitting, brilliantly into the whole scheme. Now, everything else is, I think, a sort of idea that you might have, but without convincing explanation. Well, convincing observational.
Lots of things to do.
Well, sure, but I would think that, honestly speaking, this is the case. There are people who think that some geological structures in Earth, for instance, are caused by tiny black holes that travel through the Earth crust and make the effect. Well, if you convince me and show the calculations, and if it works, it should be okay. But yeah, if extraordinary idea needs an extraordinary.
Okay, I have a question which is in relation to this discussion. If we know there is a black hole, how it influences the possibility of the space exploration? It can influence this exploration or no?
I would say in the near vicinity, I would say you could use the fact that there are some black hole related objects in a way that probably is not very, very obvious at the beginning, but surely practical. For instance, you could look at quasars, quasi-stellar radio sources. These are distant radio sources with and our best astronomical understanding of quasars is based on the model with a black hole and accretion disk and a jet and so on. And if you look for a very precise way of making astronavigation, I don't even know if this is the right term. Right?
Yeah,
but
astronavigation.
think of the way of orienting yourself very precisely in space. This would be your fixed stars.
Okay.
Clearly there, and clearly black hole related.
Okay, it can help us. Okay, thank you very much. There is a last question.
Yeah, actually, jumping into the other question about small black holes, one of the theories about Planet X, Planet 9 is that it's a tiny black hole. It's, given that, if that would be a very small mass black hole, would we observe an accretion disk around it if it would exist?
Okay. This is a good question. So let me tell you something about this theory. It has this maybe unpleasant property that it has no intrinsic scale. So you can have black hole as a solution to Einstein equations of any mass. There is no limit. It can be small, it can be large, right? And hence there is no theoretical effect that would prevent anything. And you could have the motion of the dust around, of the gas around the black hole, and this is also scaleless. Okay, so then of course the density would be different, the temperature would be different, and so on. But if you can have an accretion disk around a very large one, you could have an accretion disk around a very small one. So I think simply theory does not answer this question, because what we would expect is that there would be black holes, even large ones, without matter around, not consuming anything, and we will simply not see them. And there should be those with matter and with disks and so on. So that's why I think theory by itself doesn't tell you the answer.
Thank you very much. That was exciting keynote. Thank you, Professor. Once again. And now we will start a regular session.